Hi, I'm Oliva, and in this video, we'll be looking at the recycling of NdFeB magnets using oxalic acid leaching. NdFeB, or neodymium iron boron magnets, are the strongest type of permanent magnets commercially available. They're made from an alloy of, as the name suggests, neodymium iron and boron. They have some outstanding magnetic properties like high remanence, coercivity, and maximum energy product. Because of this, they're essential components in green energy technologies like wind turbines and electrical vehicles. And that brings us to an important question, which is why should we recycle them? Well, it really boils down to two main reasons. First, environmental and regulatory elevation, and second, supply chain stability and reducing economic dependence. To break down the first point, traditional mining of rare earth elements can be incredibly harmful to the environment. It often involves large amounts of energy consumption and creates toxic byproducts. Recycling helps us avoid this, and it also helps us avoid strict regulations related to radioactive materials like thorium and uranium, which are often found in natural ores. This quality of it ties into the climate crisis section of UCL Grant Challenges. Now, for the second point, supply chains. Right now, the global supply of rare earths is concentrated in just a few countries. By recycling magnets, nations can create a local, stable source of rare earth materials, reducing the risk of geopolitical pressure or trade restrictions. This ties into, or rather addresses the section, justice and equality, raised by UCL's grant challenges. So, how exactly do we recycle these magnets? There are three main methods currently in use: hydrometallurgy, pyrometallurgy, and hydrogen deprectation. But today we're focusing on a lesser known method, one that uses oxalic acid to recover both rare earth elements and iron from NdFeB magnet waste. So, why use oxalic acid? Oxalic acid is a dicarboxylic acid with chelating properties, which basically means it can form bonds with metal ions. And here's what makes it so useful in this process: it leaches iron by forming soluble iron oxide complexes like ferric oxalate. At the same time, it causes rare earth elements to precipitate, turning them into solid particles that can be separated from the solution. In other words, it allows us to extract both iron and REEs in a single efficient step. Here's a simplified diagram of the entire process. Feel free to pause and take a closer look. Now, let's break down each step to see how this process works in practice. We start by treating the NdFeB magnets with oxalic acid. This causes the mixture to separate into two streams, one containing solid rare earth oxalates and the other containing a iron rich solution. Following stream 1 first, the solid rare earth oxalates. These are further processed to produce rare earth oxides. Then, through a process called calcination, the oxalates are thermally broken down into usable oxides. From there, molten salt electrolysis is used to convert these oxides into rare earth alloys ready to be used in new magnets. Now, let's follow stream 2, the liquid iron rich solution. This undergoes a reduction reaction using iron powder, which converts ferric iron to ferrous iron. The result? A solid product known as ferrous oxalate dihydrate, which can be collected and reused.